Hi guys, so let's talk about section 12.1, inference for linear regression. Okay, so I'm going to assume that you've reviewed chapter 3 and this stuff is kind of fresh in your mind. We did do linear regression in chapter 3 and we were able to do things like find a regression line and things like that. But now we want to say, how good of an estimate is a regression line for a population regression line. So what we did in chapter 3 was do a regression line for our sample, but we need to make sure that that's an accurate estimate of our population regression line. And more specifically, you'll see we're talking really about slope. If the slope of the sample regression line is a good estimate for the slope of the population regression line. Okay, that's really what we're after in this chapter. So we will do, in section 12.1, we'll do basically constructing a confidence interval for this slope beta, which is the true population slope of the true slope of the population regression line, and we will also do a hypothesis test about that slope. Okay, and so there's a lot to read here. I'll let you read that. I'm not going to read all this stuff with you, but basically these are the two things we need to think about. If we took data and got a least square regression line based on a sample, is there really a linear relationship between x and y in the population? So we looked at the sample, but the question is that also true for the population? And in the population, how much will the predicted value change for each increase of 1 unit in x? Okay, and what's the margin of error? So again, we everything we did in chapter 3 was about sample data, and we want to see how that actually holds true for population data. Okay, so we want to do inference to the population. Alright, so it says if data come from a randomized experiment, the values of the explanatory variable correspond to levels of some factor that's being manipulated by the researchers. Okay. Alright, so let's look at this data here. So important that you understand how we're approaching this. In chapter 3 we looked at this actually, the two clusters. I don't know if you remember that. This was the Old Faithful geyser data. And this is the scatter plot of all 222 recorded eruptions in a month. So what we're saying is this is just for the purpose of illustrating sampling distribution of a sample slope. We're considering this to be the graph and data set that represents the population of all recorded eruptions for a month. Okay. So we're calling this our population, all right, in order to demonstrate the idea of a sample slope sampling distribution, okay? And so they're saying here that the least squares regression line for this population data is this. It is basically y, not y hat, okay? Not y hat, because now we're dealing with the actual population regression line. So it's not predicted y. This is the population. So we're going to call it y equals 33.97 plus 10.36x. And we're saying that is the population regression line. Okay? And so now what we're doing is saying, suppose we take an SRS of 20 eruptions from the population, okay? So suppose we take an SRS of 20 eruptions from the population. So I go here and I take a sample of 20 of these little dots, okay? And then I calculate a least square regression line for my sample of size 20. And what they did here is they did it 3 times. Okay, so here's my first sample of size 20, here's my second sample of size 20, here's my third sample of size 20. And these are now, you can see the regression line is y hat, because it's predicted y, because these are regression equations based on sample data. Okay, and the point here is to show you that what you'll see is the thing we're most interested in. You'll see that everything is a little bit different from the population values, but the thing we're really interested in is the sample slope. Okay, the sample slope, and the sample slope you can see is not exactly the same as the population slope. So, and that makes sense. There's sampling variability. This makes sense. Your samples will very rarely yield exactly the same slope as the actual true population slope. Okay. So, in order to know something about my relationship between my population, the slope of the population regression line and the slope of the sample regression line, I really need to look at the sampling distribution of the sample slope. Okay, and so that's what we need to look at. And so let's do that. So if we simulate, now this is a simulation, right? And this is not a proof. We don't prove the theory behind sampling distributions in this class. As you know, that's a little bit outside of the scope of our mathematical knowledge, right? But it says confidence intervals and significance tests about the slope of the population regression line are based on the sampling distribution of B, the slope of the sample regression line. Okay, and so they used Fathom and they came up with this. So this is based on the setup we had up here. They went to the population and sampled 20 eruptions and made a regression line, calculated the slope of the sample regression line each time, and they did that 1,000 times. Okay, so there's 1,000 dots here. So each of these dots represents 1B. So each of these dots represents 1B, and B means a slope of a sample regression line. All right, and so after doing this 1,000 times, you can see that this is approximately normally distributed, and the center of the approximate, in this case, it's not the real sampling distribution, is there. And so here is a normal probability plot of all of those sample slopes, and here is a histogram. Okay, and so you can feel very confident at this point that the distribution is approximately normal. And so we see this, and then what's the center of the sampling distribution of our approximate sampling distribution after 1,000 samples of size 20? I get 10.32, and this is the truth. This is the population value. Okay, and then the standard deviation is this, and you know, this is the true standard deviation. Okay, so if you think back to chapter 7, this should tell you something. In chapter 7, we said that if the mean or the center or the mean of the sampling distribution of a sample statistic is equals to the parameter, which this is approximately equal because it's approximate sampling distribution, then we can say that the sample slope B is an unbiased estimator, okay, of the slope of the population regression line beta. All right. So, in other words, we spoke about all this stuff just so that we can say, if I take a sample from a population properly, I take a good random sample, and I calculate the regression line, and I find the slope of the sample regression line. Since that slope is an unbiased estimator of the population regression line slope, I know I can trust it, and so it's an accurate estimate. Okay, all right. So all of that was just to establish that we can trust B, the slope of the sample regression line, as a good estimate for beta, the slope of the population regression line. Okay, and so let's talk about the sampling distribution of a slope. It says if you choose an SRS of n observations, that's paired data from a population size n with least square regression line so and so, right? And B be this, let B be the slope of the sample regression line. Then the mean of the sampling distribution of the sample slope is this. Okay, it will be equal to the population regression line slope. And just remember, this is important for you actually here. Y equals alpha plus beta x is actually how they write it. Okay, I don't know why the textbook keeps putting a instead of alpha, but so this means alpha here. Now this is very confusing because alpha for us means our significance level usually. Alpha here means the y-intercept of the population regression line, and then beta here means the slope of the population regression line. Okay, and so yeah, the mean of the sampling distribution of the sample slope is equals to the true population slope, and the standard deviation of the sampling distribution of B is this. Okay, and you don't have to worry about that formula. That's not something that you're ever really going to need to know or use or calculate or anything like that. Okay, as long as the 10% condition is satisfied. In other words, to calculate standard deviation of a sampling distribution, you still need to satisfy the 10% condition. Okay, for independence purposes. And then the sampling distribution of B will be approximately normal. Now, this is a hard condition to meet here. If the values of the response variable y follow a normal distribution for each value of the explanatory variable x. Okay, if the values of the response variable y follow a normal distribution for each value of the explanatory variable x. So this is the normal condition for the sampling distribution of a sample slope. Okay, I wouldn't worry about that too much. Okay, so this, and I'm going to show you a little bit later here on this graph, really what that means. And in fact, let me just talk to you about that right now. So what this is saying is the normal condition for the sample slope is true if I take any specific x value, okay, and I look at all the y values that occur at that x value. All right, if those y values are approximately normally distributed, okay, then I know that, so for each x value, if these y values are approximately normally distributed, then I know that the sampling distribution of the sample slope will be approximately normal. That's very, very difficult to check. We rarely have enough data in a graph to accomplish this little scenario here. Okay, so any case, so we have some practical ways of doing that. So practical things, and that's listed in this little step here. Okay, so any case, so that's the theory there. The theory is basically just saying if you've checked the conditions are met for the sampling distribution of the sample slope, then I can trust that it's a good estimator of the population slope. Okay, and I keep saying population slope. What I mean is the slope of the population regression line. Okay, beta. All right, so we need conditions to be met for inference. Of course, you can fit a least square regression line to any data and calculate an equation and go for it. Okay. Remember, we said the results are only useful, linear regression only works if the scatter plot shows a linear pattern. And then for the sampling distribution of the sample slope to be useful for us and all those kind of things, there's a whole bunch of additional conditions that need to be met. Okay. Remember that B and A in our y hat equation. Those are statistics, and so we need to make sure the conditions are met that those statistics are good estimators of the unknown parameters, alpha and beta. And alpha here means the y-intercept of the population regression line. Beta means the slope of the population regression line. Okay, it's confusing because they also were used in other ways. Beta was also the probability of a type 2 error. Okay, and alpha is our significance level or the probability of a type 1 error. So don't get confused by that here. All right, it's pretty confusing. All right, so what are the conditions for regression inference? We have a nice little acronym called LINER. Okay, so following linear, independent, normal, equal variance, and random. Okay, so that's the last acronym that you really have to know for this class. This is really the last acronym you have to remember. LINER. Okay, LINER stands for linear. In other words, there's a linear relationship in your scatter plot, basically. Okay, there's a linear relationship. All right. Then independent, individual observations are independent of each other. You're okay with that. Normal, for any fixed value x, the response y varies according to a normal distribution. That's this part right here. For any fixed x, this happens. All right. And then equal variance, the standard deviation y of y is the same for all values of x. Okay, so the standard deviation here, if I pick a fixed x value, the standard deviation is the same as if I pick another x value and look at the standard deviation there. How are the y values varying about the regression line for any x value? Okay, very difficult stuff. And then random, the data all come from a well-designed random experiment. Of course, randomness underlies all of the statistics that anybody ever does. Okay. All right. So that's actually very difficult. This is a really difficult set of inference conditions to meet. So we need to give you some practical tips. Okay. So we'll give you some practical tips. I'll leave this with you. This is a really this is our first three-dimensional graph we're actually looking at in AP statistics. Unfortunately for you, if you go further with statistics, there's a lot of three-dimensional mathematics in your future. Any case, so I'll leave this with you. We can wrestle with this and be unhappy with it or not, but we give you some practical tips here. So here are the actual practical tips for how to actually go about doing inference checking. Okay, conditions checking for inference for a slope of a population regression line. Okay, and so linear, you look at the scatter plot. Right, look at the scatter plot, and then also look at the residual plot. So we've done this before in chapter 3. To check the linear condition, I just check does the scatter plot have a linear pattern, and are the residuals basically randomly scattered around the line residual equals 0. Okay. Independence, you've been doing this forever. You know how to check the independence condition. If it's from sampling, check the 10% condition. If it's from an experiment, make sure that individual observations or reactions to a treatment or whatever would be independent. Okay? So we want random sampling and random assignment. That will help us with independence. And then normality, so here, normality seems really, really difficult, but here's what you actually do. Make a stem plot, histogram, normal probability plot of the residuals. Okay, so normal probability plot of the residuals, and check for clear skewness or other major departures from normality. Now, in reality, this is not going to happen very often, okay? And then you'll see a little bit later, we talk about that. Meeting this condition is quite hard, right? So the other good thing for you is for chapter 12, you are usually given the graphs that you need. You don't really, now you should know how to make a normal probability plot. We did do this. A histogram, of course, stem plot, of course. You should know how to find the residuals on your calculator. If you don't remember that, go back to chapter 3 and review how to find the residuals on your calculator. And then, this is all assuming you were given the data. If you were given the data, then you can make a plot of the residuals and check if you see a approximately normal distribution, okay? And then equal variance means look at the scatter of the residuals above and below the residual line and make sure that they're about the same. That's also very difficult. So these two conditions are very difficult to meet, okay? They're very difficult to meet exactly precisely like they're listed here. So if you see something that looks sort of okay in those two regards, you can just move on, all right? And I'm going to show you right now what that means. And then random, just make sure that your sample was taken randomly, okay? And so this is really what you would actually do. This is the practical way that you would check conditions for inference. And again, liner is there, okay? Liner is there, all right? So let's do an actual example of how this works, and then maybe this will give you a little bit more joy about how this is turning out, all right? So Mr. Barrett's class did a variation of the helicopter experiment on page 738. You can read that if you want. Students randomly assigned 14 helicopters to each of 5 drop heights, okay? So that means that there's 14 dots here, 14 here, 14 here. 14 helicopters were dropped from a specific height, okay? And there's the height that they were dropped from, all right? And then teams of students released the 70 helicopters in a predetermined random order and measured the flight times in seconds. The class used Minitab to carry out least square regression analysis, okay? Scatter plot, residual plot, histogram, normal probability plot of the residuals are shown. So they gave you all the graphs. You don't have to worry about making the graphs, okay? So just understand what they are. This would be the scatter plot, okay? This would be the residual plot, of course. And this is the histogram and the normal probability plot of the residuals. All right. So what you have to do is check the conditions. All right. So the conditions are linear. All right. And you look at this and you go, this is not what we'd normally like to see. But, this is not how a normal scatter plot looks for us. It looks like that normally. But you can see a linear pattern here, okay? There's clusters in the graph, but you can see a linear pattern. And the clusters make sense because I'm dropping helicopters from a fixed height, okay? So what we can say is just the scatter plot that shows a linear pattern, okay? And then the other thing they said we said we have to check is that the residuals are scattered around the line residual equals 0 in a fairly random pattern. So I mean, we don't really see a pattern here of how this is being scattered. So you can just say the residual plot shows a random scatter, something like that, okay? You could just do that. All right, so does it really? This is a weird example because of the nature of the data, but yeah, I don't really see a pattern in the residual plot. Okay, and both of those are chapter 3 type things. All right, and then independent, and we say, looking at this, all right, helicopters were randomly assigned to drop heights, and it's reasonable to assume that one helicopter's drop height doesn't affect another, okay? And no helicopter was used twice or anything like that. So we can just say because the helicopters were released in random order and it's reasonable to assume that yeah, knowing that one helicopter's flight time doesn't impact another, okay? Okay, we can just say the independent condition is met. The condition is met, something like that. All right. And then, so liner, what would that be? Normal. Okay. And then we look at this and we say, okay, the histogram and the normal probability plot shows that the residuals are approximately normal. Okay. So you can just say the distribution of the residuals is approximately normal. Okay, and then the last one, second last one, liner, equal variance. Okay, equal variance. And equal variance is that basically you're saying that this is happening right here. Okay, if this the residuals vary this much from 0 here, they should vary that much from 0 here, they should vary that much from 0 here. Same thing here, same thing here. So the spread about the residual line, the residual equals 0 line is about the same. It's not the same, but it's okay. So this is a condition that's very, very hard to meet. So what you can say is, we don't see any real problems for the equal variance condition. Okay, so you can just say something like there is about a similar amount of scatter around the residual equals 0 line. Okay, it's not exactly the same. We don't have that much data, but it's okay. That's basically what we're saying. So don't worry too much about the equal variance condition. Very hard to meet that condition. Okay, and then random is the last one, and we just say the helicopters were randomly assigned to drop heights. Okay, the helicopters were randomly assigned to drop heights. All right, and that's it. So that's really annoying. You've checked the conditions for inference. All right, so it says here in a little boxy woxy what I've been telling you all along. Okay, there'll always be some irregularity when you look for normal and fixed standard deviation. So normality and equal variance. All right. Then it says if you see this kind of a thing happening in your residual plot, you've got a problem. Okay, that's basically what it's saying. If you see larger scatter as y gets larger, or as what does it say? As x gets larger, as a response y gets larger, so does the scatter of the residuals. Okay, so if you have those kind of things happening, you should be cautious of doing inference, because the regression line is not a good fit for the data to begin with. Okay. All right. So estimating parameters. When conditions are met, we can do inference about the regression model. Mu sub y equals alpha plus beta x. Okay. The first step is to estimate the unknown parameters. If we calculate the sample least regression line, okay, we know that slope is unbiased, and y-intercept A is an unbiased estimator of the true y-intercept alpha. Okay, I didn't know that, you didn't know that, so they're telling you that this is an unbiased estimator of that, and B is an unbiased estimator of beta that we didn't know. Okay. And the remaining standard parameter is the standard deviation sigma, which describes the variability of the response y about the population true regression line. That's the standard deviation of the residuals. Okay, so sigma is the population standard deviation of the residuals. Okay, and we're saying that the sample standard deviation of the residuals is an accurate estimate of, or an unbiased estimate of, the population standard deviation of the residuals. Okay, and so estimate this. This seems ridiculous. I understand that. Please don't choke in laughter. It says estimate the parameters alpha, beta, and sigma. Basically, just a refresher. Can you still read regression analysis output? That's what it's saying. So remember, constant refers to the y-intercept. So this means that A in my sample regression line A is that. Okay, and then drop height equals that, means my slope B is that, and this is the standard deviation of the residuals. Okay, so they said S here very nicely for you. There it is. All right, so if you have to make estimates, you would say that B equals 0.0057244 is a good estimate of beta. Okay, and then you would say A equals negative 0.03761 is a good estimate of alpha, and we would say that S equals 0.168181 is a good estimate of sigma. Okay, and you should remember how to write the regression line from this, but you already basically did. Y hat equals basically negative 0.03761 plus 0.0057244 x. Okay, and then you should say y hat is predicted flight time. I remember all this stuff from chapter 3. Y hat is predicted flight time, and x is the drop height. This was all review stuff from chapter 3. Okay, So it's possible to do inference about any of those parameters, parameters being these, okay? Parameters being population values, remember that, parameter and statistic. But actually what we care about most is the slope. So, what does that mean? Well, y-intercept, we said in chapter 3, frequently doesn't give us useful information, okay? And it gives us nonsensical information sometimes, the y-intercept. So, the thing we're most interested in is this estimating the slope of the true population regression line. In other words, what I really, you'll see this in the next section, what I really want to know is the slope not zero? Okay, so I want something like this, or I want something like this. Anything, any slope besides zero. If the slope is zero, okay, or if it's plausible that the true population slope can actually be zero, then my regression model doesn't help me at all. Okay, then it's possible that there's no actual change in y for any change in x. If that's a plausible thing based on my regression analysis, then I don't want to do inference to the population. That's useless. Okay, so we're very, very interested in estimating or testing, doing a hypothesis test about the slope of the population regression line beta. Okay, so how do we estimate an unknown parameter? We do a confidence interval. That's how we estimate unknown parameters, and you've known that for a very long time now, since chapter 8. So the first thing we'll do is constructing a confidence interval for the slope, and when we say slope here, we mean the slope beta of the population regression line. Okay, and so this is on your formula sheet. Remember, this is on your formula sheet. That's the generic form of a confidence interval. But by now this should not scare you. You know what the statistic is we would use. That's B. That's the sample, the slope of the sample regression line. Okay, and then we use a critical value. So here, this is a T procedure. Okay, this is the T procedure. Hopefully you can remember T procedures. So the other T procedures were one sample or two sample procedures for calculating or estimating mean. Okay, so those were T procedures as well. So it's the sample slope plus or minus T star, which is based on your confidence level, times the standard error of the slope. Okay, standard error of the slope. And they give you the formula for the standard error of the slope. Again, this is not really something that you have to calculate. If you want to know what these things mean, this means the standard deviation of the x values in the data set, and this means the standard deviation of the residuals over, that. So why this works, how this works, I really wouldn't spend too much time worrying about this. For our class, this is a number that you'll just be given, okay? Or you will be given data and your calculator will just spit out the interval for you, because there's a test for a confidence interval for to estimate the population regression line slope. So there's a test for that on your calculator, so you can do that. So I wouldn't worry about that too much. You're either going to be given all this information and you just plug it in and state that the degrees of freedom is n minus 2, and you need to use that obviously to find your T star, or you can use your calculator from a data set and it'll just do it all for you. Okay, so please don't worry about that too much. All right. And that's about that. So we should just do one. Okay. And there's still a whole bunch of stuff here. Oh my goodness. Okay, so let's do one. So what does this say? Yeah, again, you really have to calculate SE by hand. All right. All right, so here's the regression output again. Identify the standard error of the slope, standard error of the slope. What is the standard error of the slope? And you say, this is the standard error of the slope. Okay, so first of all, here's the slope, and they're saying here's the standard error of that statistic. So there it is. Okay, so SE sub B is 0.00020018, and then it says interpret that in context. All right. So remember what standard error represents. Standard error says how far would, on average, would the sample statistic vary from the population parameter. Okay, and so you would say this is the interpretation. If, and this is very useful again for all of the review we've done for all of the inference procedures. Okay, if we repeated the random assignment many times, okay, the slope, in other words, if we repeated the whole experiment many times, the slope of the sample regression line would typically vary or on average vary by about 0.00020018 from the slope of the true regression line. And we always said this, the regression line that predicts or predicting, what does the regression line predict? Flight time from drop height, okay? Predicting flight time from drop height, something like that, okay? All right, find the critical value for a 95% confidence interval. This is too easy for you, but okay, let's do that. So you know how to do this. On your calculator, you're doing inverse t, and you're putting in the area. So if it's 95% confidence interval, it's 0.025 is my area. And then for t procedure, you have to put degrees of freedom, and we said degrees of freedom here would be n minus 2. And we know that there's 70 helicopters, so my df is 70 minus 2, which is 68. So I put 68 here. You must know how to do this, so you get your t star, okay? T star would be 1.995, okay? And then calculate the interval. All right, calculate the interval. So let's do that using this little formula here, okay? So I have b plus or minus t star times standard error of the slope, okay? And that is 0.0057244 plus minus 1.995 times the standard error of the slope is this thing right here. Okay, and if you do that calculation, you get the answer. Okay, I think for the textbook they used for their t star, they used 2 because they used table B or something. You don't need to do table B. Please don't do that. Use your calculator. And so they got some interval. The interval they got was this, okay? A little bit different from yours. But something like 0.0053208 to 0.006128. Okay? And then interpret the interval in context. You remember this. I'll do this one with you. We are 95% confident that what? The interval from 0.0053208 to 0.006128. And they put the units seconds per centimeter. Ooh. Captures the now what is it that we're doing here? We're trying to estimate the slope of the population regression line. Okay, so captures the slope of the population regression line beta. Okay, and you can say relating, so what does the population regression line do? It relates, again, like we said here, it relates flight time and drop height. Okay, but I will just stop there. We're 95% confident the interval from there to there seconds captures the slope of the population regression line beta. That's good enough. And then explain the meaning of 95% confident in context. So this is interpret the interval, is this conclusion to inference procedure for confidence interval. This is interpret the confidence level, interpret 95%. Okay, interpret 95%. So this says, if this is good review, if we repeat the experiment many times, okay, and use this same method, let's say this same method to calculate the confidence interval, estimating beta, okay, and we can say about 95% of the resulting intervals will capture the true slope, okay, about 95% of the resulting intervals will capture the slope of the population regression line. Beta. Okay. Yeah, so that's that. So basically what we just did is we went through and did everything. So we did one entire estimation of a sample population regression line slope. Okay, so this whole note sheet, all we've done basically is check conditions and then actually calculate a confidence interval for a slope of a population regression line, and then we interpreted everything as well. Okay, so this was a really good review of a whole bunch of stuff we've done this year so far. Okay, And what does it say? Careful, the values of t given the computer regression output are not critical values for a confidence interval. They come from carrying out a significance test about the y-intercept. So, if you look at this, these are not t star values. That's what they're saying. Okay, these are not t star values. All right. This is actually a test statistic for carrying out a hypothesis test. So if you did a hypothesis test, your test statistic would be 28.37, and the corresponding p-value for this specific situation would be 0. Okay, so that's what that says. All right, guys, I'm not going to do example 4. Example 4 is just another example here. You're given everything you need, and this says construct a 90% confidence interval. So you're going in, you're saying, oh, okay, we want to estimate this with 90% confidence level, and you do, you know, if conditions are met, you do your state, plan, do, conclude. Do your state, plan, do, conclude. All right? So state, name the procedure, what are you trying to do, plan, check the conditions. In this case, it'll be linear. Do would be actually calculate. Remember to state your degrees of freedom, and then conclude would be interpret the confidence interval. All right, I'm not going to do all that with you. I think you understand that procedure. You should do it, practice it, and then go do the homework. The homework again is slight, as usual, not too bad. And you'll see that to do the confidence interval on your calculator, you need the data. Okay, and I think we're going to do one of those where you have the data in the next section. All right, so go do this confidence interval example 4 by yourself. The completed note sheets are there, it's all there, and I think that's okay. All right, thank you.